So at the end of our previous lecture, we mentioned that we'd probably jump into the strain life approach to fatigue pretty soon. But before we do that, I do want to touch upon one more topic, and that is the topic of damage and something called Miner's Rule. It's also known as the Palmgren-Miner Rule. And so to kind of motivate our discussion, and since we have just talked about stress life fatigue so far, we're going to take a look at an SN curve and get an idea of what's going on with life and how damage would relate to that. So if you remember when we talked about our stress life approach, we talked about typically a rotating bending specimen, and we would count the number of cycles to failure. We would plot these data points, these experimental data points, on a curve, and then we would produce a best fit line for that curve, which accounts for some scatter. So I filled in the circles on this plot in red, and so you see they don't quite always all fall right on the line, and we have to kind of understand that when we read the graph, there will be some variability in it. Another thing I'd like to point out about the SN curve that I don't think I've pointed out yet is that in most graphs you plot the dependent variable on the vertical axis and the independent variable on the horizontal axis. However, it is traditional in fatigue to do the opposite. We control the stress amplitude by putting weights on a rotating bending machine or the load level in a servohydraulic testing machine. And the dependent variable, the result of that, is the fatigue life. And we plot that on the horizontal axis. So if you do statistical analysis, be careful how you identify the dependent and the independent variable. There are certain things that can change if you do rigorous statistical analysis depending on how those are defined. I just want to point that out here. All right, so again, with our alternating stress, we do these fatigue tests, we get the life, plot the curve, and then we would use this plot to estimate what the fatigue life might be at different levels of stress. So for example, I'm showing a plot here where if I was at 60 KSI and I draw this line over, I'm probably at those two dots. Maybe my line isn't perfect. You draw that over here and you'd bring it down to the number of cycles to failure, and we could determine what the number of cycles to failure were. So let me write this here. The amplitude of 60 KSI, remember for a rotating bending test that's plus and minus 60 KSI, corresponds to a number of cycles to failure of, I'm estimating it to be 2 times 10 to the 5th cycles. Remember, these are log-log plots, and so what I've done here, I've already done this, is I've marked in about where I think 2 times 10 to the 5th would be, then 3, 4, 5, 6, 7, 8, 9. They tend to bunch up over here, and then we get to 10 to the 6. Now, reading log-log plots, the experimental data, all of that has some variability into it. So when I say 2 times 10 to the 5th, okay, maybe it's 2.5 times 10 to the 5th, maybe it's 1.5 times 10 to the 5th, but we're right in there somewhere, kind of in tune with the scatter of what's going on with this fatigue data. So let's talk about what might have happened during this fatigue test. I'm going to make a plot of the stress amplitude versus time. So we started it up. There's a cycle. And nothing happened, didn't break. There's another cycle. And another cycle. And then eventually we keep going, and maybe it breaks. Something like this would probably break at some point of that on maybe the tensile side of the stress. Okay? So it breaks, and that's when we get to about 2 times 10 to the 5th cycles. We have a finite life. We're not less than the endurance limit stress, so it is going to break. And this is for 1045 steel. So this is a ferrous type alloy. All right, well, let's think back about what happened in our paperclip experiment that we talked about at the very first day of class. And if you don't remember, we can think of things through. We took our paperclip and we bent it to a 45-degree angle, and then we bent it back to a 0-degree angle. And we did that a number of times until it finally broke. The first time we did it and the second time we did it pretty much had the same result. We didn't see anything happen to that paperclip. We didn't see any cracks form, and the thing didn't break. And really, the first cycle, maybe the thing lasted 35 cycles. The first cycle and the 30th cycle, we wouldn't have been able to visually see anything different. Now we know if we would have used an electron microscope, we probably could have seen some things going on and some damage happening. But maybe on the 34th cycle, we saw a little crack start to form, and then on the 35th cycle, then that crack got really big and broke the thing. So from that perspective, from our paperclip, the first many cycles were pretty much like the ones previous to it. Maybe only on the final couple of cycles did we see a crack start to propagate and grow. Well, that same sort of phenomenon happens when you do a fatigue test. You put your specimen in a testing machine and you let it go and you load it up and you cycle it, and you go a long time and nothing happens. In fact, you can set your testing machine up to stop when the specimen breaks in two. And unless you like to watch testing machines a long time, you're probably not going to see anything happen until you get to the last 2, 3, 4, 5 cycles. Okay, it's almost kind of rare to be around a testing machine when the specimen actually breaks due to fatigue failure. Sometimes you get some indications, sometimes you kind of know, but it's kind of rare to be right there when it happens. So what I'm getting at is that for the most part, from a physical observation point of view, for our 1045 steel, there probably wasn't anything that we could visibly notice different about that specimen for the first cycles all the way up to maybe 5 cycles before 2 times 10 to the 5th cycles. And again, 2 times 10 to the 5th is an estimate from reading that graph. I'm not saying that particular test lasted exactly 2 times 10 to the 5th, but that's what we would expect it to be around. All right. Well, what does that mean from the perspective of damage? We can have an assumption that we can make. The assumption is that each cycle is equally damaging. Is that really a good assumption? I think we'll see for the most part in the context of our fatigue analysis it is. When we get into fracture analysis and fatigue crack growth, that may not be a good assumption. Things are changing too quickly with the extension of larger cracks, ones that you could visibly see, for us to be able to really rely on that assumption. We can also make other assumptions about our fatigue test, but without having any other information, each cycle being equally damaging is pretty reasonable. Okay, and that's the assumption that was used for linear Miner's rule. Well, let's talk about damage from a numerical point of view in this idea of fatigue life and damage. Let me make a little bit of room. we're going to talk about two related concepts of damage in life in the context of each cycle at our particular stress amplitude contributes equally to the damage. Okay, so we said that the life was 2 times 10 to the 5th cycles. And we can say that the damage is 100% for 60 KSI. For a stress amplitude at 60 KSI, the damage was 100% after 2 times 10 to the 5th cycles. Now, 100%, percentage is a number times 100. So another way we can say that is the damage is equal to 1.0 after 2 times 10 to the 5th cycles. Okay, and this is a thing that we're going to take, is that whenever damage is equal to 1, that is the total damage that that part can take. Now, we're going to be able to institute safety factors on life. So a safety factor of 4 on life would mean that we would stop this and say we're only going to accept a damage of 0.25. We're going to design it so that it only has that much damage. Okay, but we'll get into that later. So a damage of 1 means the lifetime of that component is used up. That's when the thing has broken. Well, if each cycle contributed equally, and we had 2 times 10 to the 5th cycles, and we want a damage equal to 1, and if each cycle contributes equally to the damage per cycle must have been 1 over 2 times 10 to the 5th. So that when we multiply the damage per cycle times the number of cycles, we get 1.0. Okay, so we're going to see this a lot. There's a reciprocal relationship between damage and life. All right, let's make a little bit more room. All right, so let's just write this 60 KSI life down again. So at 60 KSI for a cycle, the damage per cycle is 1 over the number of fatigue cycles to failure at 60 KSI. In this case is 1 over 2 times 10 to the 5th. Let's try a different value. Okay, how about 70? This looks like this would be 70. Go over to the line, I come down here. Again, this is on log scales. So 2, 3, that might be 3.5 or 4. Let's call it 4. The damage per cycle, 1 over the number of cycles to failure at 70 KSI would be equal to 1 over, what did I say, 4 times 10 to the 4th. Now, of course, if we're out here less than, well, here's 50, maybe it's about 45, 42 KSI, it doesn't fail, so there would be no damage if we're at a stress level that's low. Okay, well, how would we use this information? Well, many of the applications that we're going to look at aren't going to be restricted to just one stress amplitude. Eventually, we're going to be looking at variable amplitude loading, where we can have stress levels that are all over the place, not just constant 60 KSI plus and minus, constant 70 KSI plus or minus. We're going to have a number of cases where the stress levels are going to be changing. Let's look at a case that I call block cycle loading. It's a special case of variable amplitude loading, and let's say we have 2 cycles at plus or minus 70 KSI. And then following that, we have 1, 2, 3 cycles at plus or minus 60 KSI. And this block repeats itself over and over again. We want to know how many blocks of this repeating loading can our component sustain before it breaks. Okay, so what we need to do is we need to determine the damage per block. Well, what's the damage per block? If we can linearly add the damage of each event, then we can find the damage per block. So how much damage do we have? We have 2 cycles at plus or minus 70 KSI, and we have 3 cycles at plus or minus 60 KSI. So 2 times the damage per cycle of 1 over 4 times 10 to the 4 plus 3 times the damage per cycle of 1 over 2 times 10 to the 5th. We get our calculator out and compute that number, we can find the damage per block. And for that, I got a number of 65 times 10 to the minus 6. That's my damage per block. Let me make a little bit more room again.